Paul Coghill, and this recording is the final portfolio for the Syracuse University Applied Data Science master's degree. So, just to get an idea of my background coming into the program, I have my bachelor's degree in political science, so no real math or statistical background. I do have a little bit of programming background and experience associated with some web development, coding in Java, HTML, CSS, and JavaScript. Um, Analytics side, data side of things, very limited business experience using simplistic, basic Microsoft Excel. So, what I wanted to highlight in this video is how the projects that are about to be covered are going to associate with the key and core learning concepts of the applied data science program. So the obtaining and collecting of data, the scrubbing, cleansing, and organizing of data, the exploration of the collected data, modeling of the data, and then taking action, making recommendations based off of the modeling and the analysis. So, in order to highlight those key core learning concepts, I'm going to cover four different projects: horse racing at the Hong Kong Jockey Club, that was from scripting for data analysis; recipe classification by diet, that was from text mining; a look at the true cost of healthcare in the US, that was from information visualization; and finally, from data mining, exploring basketball prospects and projecting career success. So the first project from scripting for data analysis used Python. So that was a new programming language to me. And I decided to do horse racing at the Hong Kong Jockey Club. I decided to do this project based off of an article that I read where there was a gentleman, a bettor, who used an algorithm and prior horse racing data to successfully place bets, almost $1 billion worth of bets. So I figured that it lent itself to a data science type of problem. So it just seemed like it aligned and fit. In this case, the collection of the data wasn't a trivial task. I had to use the beautiful soup package to do some web scraping. So that was a package that was introduced in the scripting for data analysis course. And essentially what I had to do was gather all of the dates of races in order to build a URL to place the request. In addition to the date, I also had to collect the track name. There's two tracks at the Hong Kong Jockey Club, so there's an indicator for both. So collection first of the date and the track name was done manually just by looking at race schedules. Once I had that, I could place requests to get the page, and the web page essentially would, I knew there'd have to be at least one race, so I would append one to the URL, as you can see here, and it would return a page like this that would have a count of each a race kind of link. So I could count all those elements and find out, okay, there were 11 races for that day, and I would just loop over and append the race number to each one of these. Scraping, horse information, jockey, trainer, finishing times, win odds. So all of this information was scraped into lists, which was then put into a pandas data frame. So that was the collection process when it came to the horse race information. And here's just a list, lots of variables that were collected. So, again, like I said, not a trivial task. It was nice to have the web development background to know about HTML elements and CSS classes and IDs made the scraping a little bit easier. The next was the processing, the cleaning, kind of getting the data in the right setup. So we had to drop a lot of missing values, removed some of the variables that didn't provide any information, like horse number. Had to do a lot of conversions. The All the data was read in as strings, so we had to convert strings to integers and floats, date times, timestamps. Also did some coding of tracks to numerical values 0 and 1 as opposed to the string values. Also took track statuses and made them into integers, higher integers, a favorable track status, lower numbers, a bad track status. So at the end of the day, after all the cleaning, we only removed right around 3,000 rows, starting from 100, over 100,000 row set. So, definitely was some processing, but still had a lot to go remaining to work with. Uh, Descriptive statistics, we ended up with over 8,000 races, over 5,000 horses, over 200 jockeys, almost 200 trainers, and just some exploratory plots. Uh, a lot of it's simple, would make sense. The longer the distance of the race, the longer it's going to take to finish the race. The odds makers seem to be pretty successful at what they do. The lower the odds are, as you can see on the x-axis, the more likely they're to finish in first, second, or third. So just gets a little bit of an idea. There was some feature extraction that was done. I thought that it might be helpful to know the weight difference, a horse from their prior race to their current race. Same thing. How many days was it in between? These could be indicators of health and rest. Also, experience. How many races did the horse run in previously? Same thing with the jockeys and the trainers, and how successful where they were. So, feature extraction by going through the data set and doing some calculations. In this course, it wasn't required to do modeling, but I figured if I had all this information, might as well try it. So no real rhyme or reason behind the selection, but I decided to do a random forest regression modeling to generate predicted finish times. And after doing the modeling, the betting that was engaged in that would be tested was very rudimentary. $10 bets were going to be wagered on the top 3 finishers based off of the random forest prediction. Wasn't all that successful. Over 12,000 bets placed, rate of return of 1.02. So you might as well put your money in the bank. So at that point, after finding that information out based off the modeling, we decided let's pump the brakes and either collect more variables that might elicit better returns, maybe look at different algorithms that might be more successful. Also, one of the big key things was looking into varying betting amounts. There might be different bet types or different amounts to bet based off of odds that might elicit better returns. So that was horse racing at the Hong Kong Jockey Club. The next was text mining. This was recipe classification by diet. This also used Python. The reason behind this one was just very simple. You got a lot of recipes online nowadays, and you have a lot of people that are trying to follow specific diet plans that are restrictive. You can eat this, but you can't eat that. So maybe they might not try a recipe because they're worried they might fall off their diet plan, or maybe there's people trying recipes and they're hindering their, progress because they're doing things that they shouldn't be. Sourcing of the data was, again, used Beautiful Soup, so we had to scrape in. I decided to do 5 different diet types, vegan, paleo, ketogenic, Mediterranean, and standard diet. They were each sourced from specific websites individually that corresponded with the diet type. So not a trivial task to scrape 5 different websites in order to collect recipes from each. To get an idea of what was actually collected, based off of the website, a label was created for the diet type. The list of ingredients was collected in a text string. The directions as well collected in a text string on how to make the recipe. And then the title was also collected just to get an idea of what the recipe was actually going to make. So all of those were collected, scraped in using Beautiful Soup, and put into a data frame that was output to a CSV file. Exploratory plots here and text mining, not real lot to look at, but just some descriptive statistics out of this collected data set. You got 2,647 different recipes or rows collected to give you a little bit of dimensionality. And the distribution was definitely not equal. Vegan had the most diets, 664 collected. Paleo at the low end of 426. So not an equal distribution, but since we're sourcing these from different websites, there's not going to be an exact amount for each and every one, and we wanted to collect as many as possible. Some of the pre-processing that we wanted to undertake, scrubbing, getting the data into the best possible situation or setup, is going to be associated with stop words. So there's a nice thing when it comes to these text mining algorithms where you can create a list of stop words that will prevent these terms from being included in the analysis. So we wanted to make sure that any of the recipes names would not be included. So there might be in the ingredients or the directions the actual name of the diet type, keto, paleo, Paleolithic. So we didn't want those to be included. We also didn't want some measurement information. We were going to end up using naive Bayes as well as support vector machines for the modeling. And we're going to do cross-validation for the testing of the accuracy. And we were also going to test recipes, ingredients, and their directions to see which one might have a better classification capability. Some of the other stop words that were going to be eliminated to reduce the dimensionality, to reduce the strain during the analysis was measurements. So you have cups, tablespoons, teaspoons. These are going to be across the board, included in pretty much every kind of recipe. So it really wouldn't give us much information gain. We also removed numbers and fractions, since those would be used throughout as well. Now getting to the modeling portion, using fivefold cross-validation on naive Bayes, we saw the most accurate using bigrams. So that's going to be when you have different n-grams, unigram, bigrams, trigrams, where you get a little more context. Unigram is one word. Bigrams would be the two words adjacent. Trigrams, a grouping of 3 words in the text. So in this case, using bigrams, you end up with 94% when using the directions correctly classified, and we just have confusion matrices here to indicate which was predicted versus the actual and where the errors might be. Using support vector machines, it ended up being a little less successful. Best option was in the ingredient list using bigrams, almost a little over 93.5%. Support vector machines gives you the ability to tune the cost, the penalty for incorrect classifications. When doing creating a pipeline for kind of testing an optimal C value here, we ended up going with a 0.05 using bigrams on the ingredient list. 94.67 was the best classification capability. We did do a little bit of error analysis just to see, hey, on our optimal settings, where are our errors coming from? So you can kind of see the diet types and the predictions, and you can look at, what ingredients were in that list that kind of stand out. Really, in this case, we just wanted to highlight one. We predicted a vegan diet for this recipe, and ice cream comes up in the ingredient list. So clearly, the algorithm, the model, hasn't kind of learned that ice cream is associated with dairy, which is associated with an animal product. So just a way to look into things. Future analysis and conclusion, we thought, hey, this is pretty darn successful when you're in the 90 to 95 range of correctly classifying. But we did think that there was probably a little bit of bias baked into things since we're sourcing all the recipes from websites that are specific for each diet type. There might be some bias that is introduced based off of the author, and maybe that the models are picking their language that they use that is prevalent that might not be associated with food or diet. So baking in and bringing in additional instances or recipes to test and to integrate might be extremely beneficial before putting this into practice. The next project was a look at the true cost of healthcare in the US. This was information visualization. And in this class, we used R Studio, and Adobe Illustrator to design some of the visuals here. So the motivation behind this topic is just the healthcare cost. It's a heated political debate. In politics for everyday Americans, the cost is affecting everybody. So we wanted to look and see, based off of the data, could the state you live in affect the number of options and the cost that's associated with healthcare costs? And can your income level also have an effect or a correlation with the cost of healthcare as well? So just to get an idea of where the data came from, in this case, we had CSV files that were available to us. Anthem had a Google challenge where they provided health insurance plan information via CSV file, over 2 million rows with various columns associated with age, rates, tobacco use, geographic location. We also wanted to supplement this with some census information, so that was sourced from Kaggle in a CSV file as well to get some income related information, population information. Some of the scrubbing, we had to remove some outliers. There were premium rates that were 0. There were premium rates that were 9,999. These were likely missing values since they just didn't line up with anything that made sense or were close to anything else. So we eliminated those plans. We also binned plans by age and aggregated average plan costs by state so that we might be able to generate some nice looking visuals. So exploratory plots, we had to include multiple visuals on the overall poster board, which was the final product to be generated here. Very simple. We took the number of plans available to non-smokers versus smokers and just did a count. And you can see how vast the options available to non-smokers are versus smokers. We also used another plot counting the number of plans available based off of state in descending fashion. So you can see the number of plans available in Florida are much greater than in Delaware. And you can also see it is also gradient scale colored blue. It's nice to have a lot of plans available where it is red in the event that you have very limited plan availability. The next visual is taking those binned age groups and looking at the average cost of individual plan premiums via violin plot distributions here. So it makes sense. The older you get, the more expensive plans are going to be. You can also see that the bulk of the plan costs are going to be on the low end. With the older you get, the elongation, the more verticality of the distribution. You can also see these a little bit more expensive plans here start to also elongate up the older you get. Next, we're going to move to some scatter plots. So we just wanted to look at how the average income per capita in each and every state might be associated with plan rates. So you can see this positive linear relationship as you live in a state where you have higher income levels. The cost of healthcare is also higher. Adobe Illustrator gives you a nice option where you can kind of play with some of these data points. So not to make it too complex or confusing, we just labeled some, but not all of the points with the state name. You can see Alaska on the high end, for both income and cost. Next, we do another scatter plot, same thing, but it's going to be the number of plans offered by population here. So you can see, again, that positive linear relationship. The more population the state has, the more plans that are offered, which would make sense. A more diverse population is going to need more flexibility and options when it comes to plans. Also encoded in on here is the rate. You can see the larger the point, the higher the rate, average rate is. Same thing, the darker the red, the higher the cost is. So encoding a little bit more information on that scatter plot as well. The key visualization here was a map that was created. So you have the dark red to indicate the high average plan cost per state. The darker the blue, the lower the plan cost. And Adobe Illustrator, again, gives you the nice option where you can highlight and kind of call out some of this information. So you can see we added in some text associated with Alaska being on the high end and their average cost. And you can also see in Mississippi there, you have the lowest average cost plan of $135. So just a nice way you can see the entire country and how average costs play out. The final product here is a poster board, and just some things to look at. We've integrated all of those previously seen visualizations, and we've laid it out in what's known as the golden ratio. You can kind of see how the left side is a larger portion. You have the lower right hand corner, and then it almost like spirals in. So that was a concept that was new. You can also see that the font type is consistent throughout, and the color scheme is also consistent throughout. With larger, the larger the font, the larger the visualization, the more important it is. So that was no modeling necessary, no additional information needed when it came to that project. The final project to talk about is from the data mining course, exploring basketball prospects and projecting career success. And essentially the reason behind this one was just I like basketball. There's only so many players that come out of the NCAAs, the college system, that make it into the pro system, and selecting successful players is going to be key to team success. So collecting it, simple copy paste into a CSV file, collected college statistics as well as biographical information, age, weight, various things like that. We did want to have an evaluation metric, so we took professional players' win shares, which is a composite of both offensive and defensive statistics, which tries to divvy up credit for team success. So that was kind of the prediction measure. We wanted to have high win shares. So based off of the data, we also collected NBA statistics and win shares. So any players that didn't play in the NCAAs, we had to eliminate from the data set. So we had international players that had to go. Any college players that were injured and never accumulated NCAA stats had to be eliminated. And we also had to cap off the data at 2006 because there were high school players that would have been included prior to that. So descriptive statistics, we ended up with over 700 NBA players and 53 prospects that were going to be looked at. We did have to do some cleaning of the data. There was positional issues, some power forwards were listed, as well as forwards were listed, guards and shooting guards and point guards. So we just made it consistent across the board when it came to positionals, as well as classes. You had seniors and sophomores and freshmen. Some of them had asterisks, some of them didn't. So we just made it consistent across the board. We also did some binning. We took the quartiles of the win shares and put them into low, medium, high, and very high. So we just kind of binned out those numerical statistics. So doing some exploratory statistics, we first looked at some of the biographical information. So high win shares was correlated and associated with low age. Same thing the higher your weight, the more likely you are to have a high wind shear. Looking at the statistical variables from the NCAA, we did normalize them to a per minute level. So you had blocks per minute, points per minute, and steals per minute, all in a positive linear fashion. The more you have per minute, the more likely you are to have a high wind shear level. And then personal fouls was a negative relationship. We did association rule binding to see what variables might be together that could indicate high wind shear level, and the modeling ended up finding different rules, and we just listed off some of the the future prospects that would fit those rules. We also did some clustering that really wasn't too beneficial here, didn't really elicit much information. Other modeling that was done, Naive Bayes, 41% correct player predictions when it came to win shares. You can see some of the names of the players. K Nearest Neighbors doing kind of a vote on the likelihood of win share classification. Again, we get a list of 16 players in this case that had very high win shares. Random Forest, the ensemble approach to look at very high win share prediction. Again, a listing here. Support vector machines was also used, trying to draw that hyperplane, that boundary between classification to get high win share predictions. And we had 16 players predicted. At the end of the day, the predictions, were in the ballpark of 35 to 41% correct classification. What we decided was take kind of an ensemble of all of those algorithms. Anybody who had high win shares across the board, we recommended to pick. And 3 of the names out of the 4 are known names after their rookie season. So it's nice to see that. At the end of the day, these projects, well, not all of them required all of the core concepts to be applied. It does indicate a level of understanding of what those core concepts are and them being put into practice, of the obtaining, collecting of data, the scrubbing, processing, and cleansing of the data to get it into the right form, the inspection of the data via descriptive statistics and exploratory plots, the modeling of the data, as well as making recommendations based off of that modeling. I appreciate your time.